We got to start it off with a 3, 2, 1.
Let's go.
Alan Morgan, I like it. Came in on point, sir.
I'm glad to be here.
It's you know what? It's really good to meet you in person.
Great. Yeah.
Right? We've done a Zoom. We've learned a lot about Bell Geospace. We learned a lot about gravity and its importance in the industry. And I know for sure the industry is seeing value every time they dig into the gravity data and the magnetics. They're looking at the information that you guys are collecting, the data you're collecting, and then tying it into geochemistry like GeoMark does. They're integrating it into their workflows. They're integrating it into their assets. You guys are providing value in the Permian Basin. Tell us a little bit about yourself, just Alan Morgan, highlight, introduction, and then specifically let's dive into the Permian and ultimately into your little presentation.
Yes. So my name is Alan Morgan. I'm a geophysicist with Bell Geospace. My background is rooted in geology. My degrees are in geology and hydrogeology. So that led me into a career that got an entry at a low time when I was assigned to do gravity and magnetic work for Fugro and Gravity Magnetic Services.
Right on.
And that has sparked an interest in geophysics and things that are beneath the ground that you cannot see from the surface. And it's amazing when you start to increase resolution, the differences in scale, the things that you can see.
Yeah.
That range from the regional down to the prospect level. So It's quite exciting to be able to see new data over old basins, and then when you can find new information.
Man, tying that to production, tying it to where people have drilled, where successes are, and then you're seeing the contrast of gravity specifically, like in the Permian Basin, gravity specifically, how it's changing, the shapes it makes, how it's correlating to the wells, how it's correlating to the information that we have from all these other types of disciplines or other data points that we have. Can you walk us through just the acquisition of the gravity data that's in the Permian Basin that you guys have, the process of that, and kind of what the data is representing?
Yes. So basically, gravity is collected from the ground. Historically, it's been collected from ground instrumentation. With gravity gradiometry, which was historically developed for subsea navigation for submarines. Mm-hmm. It's a passive system that detects density contrast in 3 directions. So it's seeing the change in density over space in, like I said, X, Y, and Z dimensions. So we fly a Basler, which is a converted DC-3. They've added new avionics and Pratt & Whitney turboprop engines, so it can fly slow and steady and low to the ground. And it collects very stable data that can be interpreted into the subsurface depending on the size and shape and density contrast.
So this plane is kind of belly up, how it flies, right? It kind of flies like that.
It's not exactly like that. It's pretty not flat and stable.
It is pretty flat?
Yeah.
Okay, I thought it was favorable because it did kind of have a tilt to it. But I've seen pictures of these things, and it's like World War II era. Like
some of the original airframes are back to the 30s, and it can present challenges on getting into countries that have arcane laws that don't recognize that the plane's been refit with new avionics, and it comes out of the assembly line as a new plane according to the FAA.
Now, the amount of data that you've collected with the gravity gradiometer, is that the
Yes.
name of the machine? The gradiometer that's in that plane, you flew it over a section of the Permian Basin, 100 square miles, something like that?
At least, yes.
Sheesh.
It's about 40 by 50 kilometers, 40 kilometers east-west, 50 kilometers north-south. Most of it in Reeves County. And we saw things that we didn't expect to see. That's what makes it more exciting.
Yeah. So you got the publicly available gravity data, right? And that's surface equipment.
Yes. It's a legacy data set that there are still people that acquire data to infill it. And that does a really good job at defining the overall basin geometry. It picks up where some of the shelves are. But we take it to the next level by being able to see fabric, seeing a weathering surface and weathering patterns, fault dissolution collapses, all kinds of things that sometimes are missed by even 3D seismic.
Man. So the publicly available gravity data, that's a gradiometer that's sitting on the surface, and then they move it and
not a gradiometry. It's only seeing one direction, which is down.
Oh.
Yes.
And it's a so they take it out to a location, they get the XY, they run the machine, collect the data, and then they move,
To another
do it
station.
to another station, they do it again.
Yes.
When that one dimension reading happens, how much rock is it looking at? How much of the crust is it
Well, it
actually?
sees the cumulative effect. You're looking at the full acceleration of gravity at a specific point, which is
From the core to
9.8.
the crust.
Yes, it's the cumulative effect.
Wow, that is freaking cool. Now, okay, so you said one dimension in the gravity kind of old legacy data as you mentioned. When you're flying and you're getting a constant reading now over that whole area on a line for 40 kilometers, that machine's running constantly.
It is.
It's a
Now, we downsample it to 1 hertz, which is the instrument is traveling, the plane is traveling at about 60 meters per second. So we're getting a unique reading for all of our channels every 60 meters, depending on the speed of the craft. But I mean, that's an average speed, 60 meters a second.
Man, okay. So and you specifically said density.
Yes.
That's how when you see data, when you see gravity, you see density of rock
Yes.
or density of the crust.
We see density contrast. So, for example, a flat lying rock that has no relief will not produce a signal. However, if you put an offset in it, that will produce a perturbance, which is lateral density contrast that will be measured.
Okay.
It does depend on the magnitude of contrast and the amount of offset.
Man. Okay, so you ran this 100 squares or 40 by 50 kilometer run in the Permian Basin, Delaware Basin side, Reeves County, over the Grisham Fault, over the Mid-Basin Fault, and then south of that, north of that. You guys have a nice big footprint in that county of solid. What was the line spacing?
100 meters. The lines are flowing north-south. Every 100 meters, we had a new line, basically mowing along from north to south.
How long did that take?
It really didn't take that long. It was over in just a few weeks.
Wow.
Yeah.
So he's just running lines, getting fuel, back up there, running lines, getting fuel. And as long as he keeps a steady pace, the machine's doing the cycle and it's capturing that data.
We also have to monitor conditions, weather,
Okay.
Also with solar intensity, you get more thermals, and which leads to vertical accelerations. We have a cutoff for depending on what the field crew is monitoring on our actual flights. If we reach a certain threshold, we'll have to call it a day because the data will just be too noisy.
Is that right? You
Yes.
can't deconvolve the...
Well, we want to reduce as much as possible of any noise source. So
you say, hey, go take a break, come back tomorrow.
flight the next day. Otherwise, it's costing us too much money for reflights.
Sheesh.
Yeah.
Wow. So you've had data sets where they come back and you're like, no, you got to refly this.
It happens on occasion.
Wow. I mean, that's the point of the industry being 100 plus years old, or gravity being what it goes back to the 40s or something. When were we getting those?
Well, actually, before that, the grandfather of the gradiometer is the torsion balance, and that was there were instruments being developed in Germany in the 1920s and before. So
What
we
were they
actually
using
have
it?
one in our office.
Is that right?
Yes.
Dang it.
But that one single point for a torsion balance, you would literally have to set up the instrument, stabilize it, level it, and put a shed around it so that the effective wind wouldn't affect it. And it has to set for 12 hours before they can get a good, quiet reading and then move it to another station.
Now, why did they even make that?
It saw using a pendulum type system. It saw the change in gravity in lateral settings. So they were detecting salt domes with early torsion balances.
Whoa.
So before that, a lot of explorers they looked at hints in the topography,
Right.
a local swell or something
Right.
that keyed them in onto a local structure.
Right.
But what we're going to get to here in the Permian, the first discovery well, they weren't looking for oil; they were looking for water.
Nice. Yeah. Hear that a lot.
Yeah.
Hear that a lot. We're out there drilling for water, and this is probably in the 20s or something.
1903 actually.
1903.
The gentleman who drilled this well was a county commissioner out of Toyah, Texas. His name was J.D. Leatherman. And the railroad, the Texas and Pacific Railroad, needed water for steam engines. They needed a good supply of water. And so everybody who had acreage out here were looking for a supply to get water to not only feed their cattle or livestock, they also tried to sell excess to the railroad.
Wow. That is pretty cool.
Yeah.
So so that makes sense. Now so the original gradiometer was in Germany was for salt domes. They were looking for
Or any kind of subsurface structure. They were looking for anticlines, and salt domes were a big. They were a big target. They're kind of like the bright spots before seismic.
Oh man. All right. So do you have a flash drive and you want to go through some slides, or you just want to talk about the deck?
Let's talk about the deck. You have that loaded?
We are in the Permian Basin. We're looking up at the screen. This is an old Texas Railroad
These
Commission.
are some of the first geologic maps produced in the area, and as you can see, we're looking at a map of the projected path of the Texas and Pacific Railroad. Pope and his expedition in the 1850s, they were looking for water supplies. I mean, originally you had
to get on the mic.
Oh, sorry.
We can slide. You can slide the mic over.
Okay.
Yeah, so you can see, or however you want to do it.
So originally you had the overland stage route coming through this area for traveling west.
Okay.
And this was the earliest expeditions were trying to designate a path for a railroad to come through, which was the Texas and Pacific.
Whoa.
So they were looking for water.
Yeah.
They were looking for other critical minerals, and at the time, sulfur and water and salt, those were all critical minerals.
Wow.
So the first, prior to 1901, basically you didn't have much production. I mean, you had Spindletop well that was drilled in East Texas.
Right.
But there was not really much of a prospect to find hydrocarbons out here in West Texas. So a lot of the sulfur, there were some sulfur occurrences that were observed, and there was a bit of salt that was historically mined and carried across the border into Mexico from these salt flats.
Yeah.
But it was a very inhospitable area to live. I mean, the natives, some of the archaeological sites that are in this area that are where the Rustler and Castile formations outcrop, where they have these rock shelters and open caverns. I mean, that water, the locals were adapted to it, but you would get the quick step if you drank it if you were passing through. So it was a very inhospitable place to travel through, and people probably wanted or would get to get the heck out of there as quickly as they could to greener pastures.
Wow. Now your data set is Reeves County, so we're going to dive into this area right here. Okay. A-Train, let's switch it to a slide that's got a zoomed in version of where we're going to be talking about. Man, this is...
We've already kind of touched on this, but if I can talk on it again if you want to.
No, let's jump into where the location is and look at the data.
This is looking at springs and sources.
Do you have a copy of this presentation of you going through each slide?
I don't have it recorded, but I gave it live in Midland.
Okay. So you give this presentation normally? Keep going, A-Train.
So this shows the surface geology and basically how the earlier explorers would use well ties to try to kind of infer what the subsurface would be before seismic.
Now with surface, what do you need to know about the surface that affects gravity?
Well, obviously the first density contrast that's going to be picked up from a plane is going to be the ground surface.
Yeah.
And we will often do a terrain correction that attempts to minimize the effect of that. It's impossible to do a full terrain correction because you do have changing lithology at the surface. So, for example, if you had a massive limestone that didn't have much porosity, that density is going to be quite high. But if you have an unconsolidated sand that basically you pick it up and it just falls through your fingers, that's going to be quite low density, around 1.8, 1.7 grams per cubic centimeter.
Do you do like surface, like 10-foot holes that you're sampling what the rock is? Or
we don't necessarily need to do that. Quite a bit of that work has already been done.
Sure.
But if we see something that stands out, such as we saw in this survey, there were things I wanted to go check out and see what was going on, because looking at the surface geologic maps, there wasn't a really good explanation for the amount of density contrast that we saw.
Wow, so, right on.
Yeah.
A-Train, let's advance. Keep going. I want to see the data. Where we're at here.
This is still talking about the original well.
Okay.
Well, let's talk a little bit about this one. Go back a slide. Yeah, to the one that shows the well. One more. This one. So this is talking about the Leatherman well and how he encountered oil at basically 170 feet below the ground surface.
Wow.
It actually came with after drilling. It came up into the to the near surface. The pressure was enough to bring it to within 30 feet of the ground surface.
Wow.
But it was a water well, and it was not intending on finding petroleum.
Of course.
So this well, and drilled in 1903, they didn't necessarily have a use for oil at that time in the basin, and the grade was not that great. So they sold this well in Pecos to grease windmills. So now you can
I
go
love
next.
it. All right, A-Train, let's advance.
So this is a descriptive log of the
Surface
rock
mostly
that they,
gypsum,
yes.
gravel. Okay, so
blue
you take that
clay, hard
information.
sand, blue clay. Now, what they didn't necessarily match what is actually there as far as a true descriptive formation
Sure.
description. There was a lot of just basically material analysis,
Yeah.
not necessarily formation analysis and provenance. So what they missed is that a certain amount of this hard sand was most likely rustler or
Some kind of
there's
Cretaceous
also a bit of
thing,
a Cretaceous limestone in the
Yeah.
area. There's
Man.
Cretaceous gravels, and there's also unconsolidated sands and gravels mixed in with that. So at
Cool.
the time, they probably didn't have enough descriptions of the local section to know exactly what they're looking for. This is kind of more of an engineering approach to figuring out what is holding the oil and how to get it out.
Okay. All right, let's advance.
Yeah.
Okay. We are now we're dived in pretty good here. We're looking at
Yes.
well spots on a map. You got two things highlighted: a cluster of old wells here. That's the Leatherman area.
Yes, this is
Nice.
actually a close-up of the Pamela Field, which is what the logs or the database, Texas database, described this field as upon its re-entry in 1980. So 1980, people came back in. They still didn't have good geophysics because seismic is still not going to give you a great image at 150 feet below the
Yeah,
ground
yeah.
surface. So these guys were just trying to repeat an earlier success. Now, before these guys came into the field, there were a few other attempts to try to find where this oil was coming from, to find any
Sure.
significant accumulation, but they were met with very little success. The first attempt came from an unnamed California company, came in later in 1903. They drilled 1.25 miles to the southwest of the original Leatherman well.
Mm-hmm.
They didn't find anything.
Wow.
And then they came in closer, and they only found the traces of oil.
Wow.
And as we can see from the 1980 redevelopment, where we defined 2 new clusters, that was still
Closeology,
maverick, or
yeah,
I mean,
yeah.
it was a
Wildcatting. Yeah.
wildcatting 101 right here. So,
All right. So we're gonna see gravity, it's intense gravity survey right here under these wells.
Yes.
Okay. Let's jump into that. Let's look at some gravity and see what you see. I want to hear what you see.
Next slide.
I can't hear y'all at all.
No problem.
Just watch my hand.
And
Keep
keep
going.
going.
Keep going.
Yeah.
Keep going. Oh, I like that map. Keep
Yeah.
going. That's basic geometry or an expectation of
Yes.
this. Keep going.
Keep going. And more. And more.
Here we go. We're getting into the
Getting closer.
geophys.
Yeah, a little more. Not
Okay.
yet. Keep going. Not yet. This one either. That's
Keep
outcrops.
going. You're looking at the geology. There's the size of this
Not
thing.
quite yet. This is some of the earlier surveys that led into that.
Fly in the plane.
Here we go.
Here we go. All right.
Backup one.
Oh, that one's probably pretty good,
Yeah.
huh?
Well, this is fine. This is
Okay,
this
yeah,
shows
right here.
the same clusters of wells.
Okay.
So
Okay.
the slide that you see on the right is the vertical gravity the vertical gravity component, the TZ, which is what if you had 60-meter sampling across the entire survey area at the so of course above the ground 80 meters.
Yeah.
This is what you would see from our data. So we see some complexity in looking at the TZ.
So when you see this image, the dark areas, the light areas, what do
The
you see?
reds are the warm colors are at an anomaly high.
Okay.
Which it's looking at more dense rocks
Okay.
underneath that site. And the green and blue colors, which is off the scale here, we do have green here. The cooler colors are going to be your gravity minima. And we see that when we look at the gravity gradients, when we look at the XX, the YY, the ZZ. The ZZ is a vertical gravity gradient. It's in the down direction. And we see the two clusters of wells. And they're
Yeah.
on the flanks of, first, the largest anomalies are actually flanking the field, defining the northern and southern boundaries.
Whoa.
And
Of a
then
low
these
density.
other anomalies that are kind of coming into it
Uh-huh.
are actually weathering structures, or they're the result of dissolution collapse that has actually started to kind of branch off of the original dissolution collapse. And I believe this is where we have compartmentalization of this reservoir.
So the gravity data is picking up near surface karsting.
Yes, and the result of karsting, which is the final product, would be dissolution collapse. So as karsting develops, first you form a void, and then after it gets to a large enough size, you collapse.
Yep.
And that collapse creates accommodation space, and the next thing that you're going to have coming in there is whatever available material is being distributed along the surface, such as sand, windblown dust, gravel, whatever
Wow.
is nearby.
Super
And-
porous,
yes,
super permeable.
depending on your sedimentation. Yeah.
Wow. Gosh dang. Okay.
So I've visited outcrops in the area where the sources of the largest anomaly highs. You do have some areas where you have limestone outcropping at the surface.
Really?
And in these blue areas, they're actually further to the southwest, there's Burnt Rock Hill. It's actually
Yeah.
a topographic positive, but it is almost entirely composed of sand and gravel. And it's the result of how it got there. It was filling this accommodation space from this large-scale dissolution collapse.
But you got a sand that's making a topographic high.
Because it's been windblown and eroded around it,
It's been
it
piled
left
up.
the gravel up behind because it's hard to erode. The dominant erosional at the surface right now is windblown.
Interesting interpretation on how the sand made the topographic high.
It was
when-
perplexing at first.
Yeah, because you got the void, you got space, you would think it just, you would think intuitively it should go into the lower parts right away, but no, it's stacked
And
up.
when we first saw the anomalies, that was the first thing we look at: is there a correlation to topography?
Mm-hmm.
And only in that one area around Burnt Rock Hill, we saw a topographic high, but it is intense anomaly low that you could not explain. Even if you applied ridiculous values for a terrain correction, you couldn't get rid of it. So that means it's not only at the surface, but it extends deeper into the surface.
So when you're looking at near surface data like this, are you somehow taking out like where the gravity is actually measuring near surface, or is this still the total volume?
It's still a cumulative effect, what we're seeing.
Wow, and the surface geology is totally matching up with these anomalies, but
But it also redefines the surface geology, because the old maps didn't quite get the full answer.
wow.
I mean, we do see fossiliferous limestone along the edge that I assume is Cretaceous in age. And then we also have, like I said, the sands and gravels that are infilling it. So
Wow.
that also brings up a question: when did this dissolution collapse start to occur?
Yeah, that's
So,
right. That's right. Man, Alan, I could sit and talk about this all day, but we have podcasts and we're going to get to shuffling in and getting more shows in. I would definitely like to, if you're up for it, for some of this stuff, to do a podcast and listen to that whole story. You have all the history put together, and the idea and the fact that the gravity data in a large 100 square miles or 40 by 50 kilometer area, the gravity is seeing the near surface complexity, which drillers are wondering, what's going to happen when I hit 200 feet here? Am I going to hit oil?
How far do they need to put casing down?
Right.
Yeah.
So the application of this is huge, and you have just a small footprint. It's not a small footprint. That's a large footprint in regards to like a seismic survey or well coverage. Like, you guys are collecting a huge area pretty inexpensively,
A lot cheaper than 3D seismic acquisition.
incredibly accurate. It ties to the geology of the rocks that are at the surface, and it has an implication of drilling
It also
costs.
helps to discreetly define where velocity changes are happening that are
To help
shallower
with-
than you can even get a fold of 1 in your seismic.
So when you go to try to start processing and calibrating seismic data, if you have it, this is helping to calibrate that model.
Yes,
Alan Morgan, thank you, sir.
you're welcome.